Hello, I'm HYO. Today I'll talk about this paper called Improved Conformalized Quantile Regression. So this is the paper from this paper. Yeah, and this is published in I think is last month. So this is a very recent paper. So okay, so let's talk about it. So before we talk about the new content of this paper, we should know some background knowledge of this paper. So the first thing is the inductive conformal prediction. So if you watch my report practice before, I talk about many times about the inductive conformal prediction, or sometimes I talk this as the split conformal prediction. So this general outline of the ICP for a data set, the xi is the feature and yi the response variable as follows. So there are several steps. So the first one will split the data to three exclusive data sets. First is training data set, and the other one is celebration set, and the third one will be the training data set, and here we'll call validation, but it's the same thing. And the second step, we'll train a machine learning model for the training sets. And next, we'll have a uncertainty, notion of uncertainty, and also it is referred to non-conformity score function. So you can see here, the most basic and widely used for non-conformity score function for regression problems is the absolute error. So which is given by the absolute value of y minus f of x. Okay, so after we got the non-conformity score, and for each element in the celebration set, we apply the function to get its non-conformity scores, and we'll use the miscoverage of error rate and compute the Q hat, and to get a quantity of the non-conformity scores. And we're given the Q hat calculate on the previous steps and get the prediction interval in out of samples given by a lower bound and the upper bound with the y minus alpha coverage guarantee. So because we got this non-conformity score, we get this, and we after calculating for Q hat for celebration sets, the prediction interval will be this one. The lower bound will be f of x minus Q hat, and upper bound will be f of x plus Q hat, and also the x is the test data. So we can find that. This prediction interval's average length will always equal to 2 times Q hat. So this is not adaptive. But also this for this inductive conformal prediction, it has the marginal coverage guarantee. So it says that suppose the D or IID samples, if we construct the prediction interval as indicated above, the following inequality holds for any non-conformity score function S and any alpha. So we'll get the probability of y belongs to this prediction interval will be larger or equal to 1 minus alpha. So this methods guarantee the marginal coverage, but it is not adaptive because the average length is always 2 times Q hat. Okay, so the next background knowledge will be the quantile regression. So in a regression problem, we attempt to find the parameters theta of a model via the minimization of sum of square residuals for a training set. We will get the minimize the sum of the square of the f of x minus y, and we plus this one, which is the potential regularization. And also we'll appropriate the Q alpha. The conditional quantile Q alpha x is given by island f of y, which is given by f of y given by x is larger or equal to alpha. And this so this true conditional distribution y given x is by minimizing the this objective. So we'll be minimize the sum of the for f of x I yi plus the positional regularization. So the fall is a quantile loss. It is also called a pinball loss. So the loss function can be mathematically expressed as that next one. Okay, so it is suggested to train a model for half of alpha and 1 minus half of alpha on training data to obtain the 1 minus alpha conditional coverage. So the prediction interval will be lower bound will be the q half of alpha, and upper bound will be q hat 1 minus half of alpha. So the prediction intervals for quantile regression, this is adaptive. But the over forecast or under forecast, you have a different cost of depending on application. So a combination of alpha conditional quantile, it should be used to get more conservative lower or upper bounds with 1 minus alpha coverage. Yeah, because sometimes the lower bound or upper bound will become too large or too large or too small. Yeah, and it needs something to become more conservative. Okay, so the next part will be conformalized quantile regression. So we call it the CQR. So the CQR grounds granting QR intervals with ICP techniques on the distribution sets to ensure a marginal coverage. It inherits the adaptive intervals which marginal coverage guarantees. So the non-conformity score function will be the maximum of the q hat x minus y or y minus q hat y minus 1 minus half of alpha. Yeah. So after calculating for this q hat, so the prediction interval with 1 minus alpha marginal coverage guarantee were given by the lower bound will be q hat half of alpha minus q hat, and the upper bound will be capital Q hat 1 minus 2 alpha plus q hat. So this celebration step of CQR will become lax of adaptiveness. It does not depend on the data in any form, and it's just a simple combination between the naive method and the QR. So to solve this problem, in this paper we'll call this method or improved conformalized quantile regression. We'll call it ICQR. So the idea of ICQR is to do the k conformal steps instead, one per each group. So we can compute each Euclidean distance between observation and cluster, then using the k-means. So also they have two. So do the k-means, they have two conditions. The first, the features must be scaled, since the distance is scale dependent. And the other one is each feature has a different predictive power upon this response variable. So let me just talk about the k-means. The k-means is a clustering algorithm that attempts to minimize the following objective. So will be the sum of I from 1 to k and x belongs to Si will get x minus ci squared. And k is number of clusters. Si is the cluster set I, and ci is the centroid of cluster I. And this distance and this one will be Elutian norm. So the k-means relies upon to the hyperparameter k to define a number of clusters before. So we must select the criteria to find the potential best k. So we suggest the fraction of variance is explained. So will be expressed by this one. The Ni will be a number of examples in cluster I, and mu denotes the feature mean. So we can get the k-means algorithm. So we can get a C11, C21 to CK1. This is the initial centroids efficiently randomly assigned. And the output will be k clusters given by layer centroids that minimize this one. Okay, so we set the coverage to false, and t was set into 1. Okay, so we'll assign each observation to the cluster with the nearest central I given by this function. Okay, so we'll collect the SIT will be this one. We'll find the SI will be the cluster I. Okay, so after we get each cluster S1 to maybe to SK, because it's from 1 to K. Okay, after we find it, and we'll add the T to T plus 1, and also we'll get the new centroid CIT T plus 1, and we'll get this new centroid. Okay, so if the CIT plus 1 equals to CIT, and then we'll stop this. Otherwise, we'll do this loop again. We'll do another SIT plus 1, and then until the CIT plus 1 equals to CIT, and then we'll find the k centroids C1 to CK. Okay, so this is the how the k-means works. Okay, so before we talk about our methods, we will talk about the permutation importance. So because we just talked about these methods, we have to features must be scaled. We have to scale the features, and so that we have each features we have a different predictive power. So this permutation importance is to do this one. Okay, so the input will be the data set and the model, and the performance measure M and R repetitions, and outputs will be D feature importance I1 to ID, because they are D dimensions. So we split data to two sets, training sets and validation sets. Also, we call the validation or the test sets. And we train the model on the training sets. We compute the baseline error score on the test sets using the performance measure M. So for every dimensions, and we do R times, we permutate the column J on validation X sets to compute the permutated error score. So using the measure M, and we can get the triangle J, which is the absolute value of the base set error minus the permutated error score, and we can get the IJ from J from 1 to D. Okay, so this is the permutation importance for each features. Okay, so next steps we introduce our new methods called improved conformalized quantile regression, which is called ICQR. So okay, this is not clear, so I just show you on paper. Okay, let me show you on paper. Okay, I think this one will be clear. Okay, so the input will be the 3 normalized sets: the training data, celebration, and the test data set, the miscoverage error rate, and the explain variance, and maximum number of cluster K, R repetitions, and a model F. So output will be adaptive intervals. So there are the five big steps here. So the first big step will be estimate the conditional quantiles with quantile regression. So this is not hard. We use the quantile regression to estimate the conditional quantiles of the half of alpha and y minus half of alpha to represent it as the capital Q hat half of alpha and capital Q y minus half of alpha. And the second step will weight the x sets by the feature importance for each feature's I1 to ID. So first we have to get the I1 to ID from the algorithm we just talked about here. And then we get the I1 to ID, and we'll get the S star training data and S star celebration and S star validation. And this column of the X star training data will be the column of X training data times the II. Yeah, so the same as the celebration and the test data for each feature. So we will get the completed of X star training data, X star celebration data, and X star validation. So the third big step will select the K for the K means. That means we want to select how many groups for the K means. So okay, so we just set from K from 2, and we'll set the best one will be false. So we have the loop here. So if the K is smaller than capital K and the best K is false, then we'll apply the K means into algorithm 1. Is here for this K means algorithm, and on the X star training, and we compute the this sigma K. This sigma K is here. Sigma K here, this one. I just showed you before. Sigma K here. Okay, so if the sigma K is larger than sigma, so the best one will be true. And we'll store the cluster centroid C1 to CK. And for else, we'll just add the number of the groups. Okay, so the fourth step will compute the Q hat 1 to Q hat K. So this 1 to K is for each cluster. Okay, so here we have the S1 to SK, which are empty sets, and we'll have a loop here. The first loop we'll do the minimum for each celebration set to find the smallest one for this distance, and we can get a S1 to SK from this one. And also, after we find this one, we can get the quantile for each cluster. So which is q hat 1 to q hat k. And so the last one, we have to prediction interval on the new data. So for each test data, also we have to find the minimum of the distance, and we'll get is the prediction interval. So this is the whole steps for improved conformalized quantile regressions. So we just do the k-means for each group for the conditional coverage. Also we do the feature importance to every data, so that we have this improved conformalized quantile regression. Okay, so the last part is the experiment for this paper. So it applies the ICQR, CQR, QR, and ICP for the 3 data sets: block feedback, Boston house price, and bike sharing. And use the feed-forward neural network with 3 output neurons to estimate the quantile regression. And it trains 100 times to reduce the associated variance. And also the 50% for the training data, and 25% for the celebration data, and also we have the 25% for the test data. And the coverage will be 0.1, and the sigma k will be set to 0.9. So we can get the results from the paper. Okay, so here is the 3 data set here. So the block feedback has 60,000 of data and with 280 dimensions. And Boston house we have 506 data and with 13 dimensions. And this is a bike sharing for 70,379 data and with 70 dimensions. So the first one, this is the block feedback, and this is the feature importance for each features. And there is a threshold fraction variance for 0.9. So we can get we have 9. If we have 9 clusters, the variance will become to 0.9. So in here, for this data, we have 9 clusters for list analysis. Okay. So we can get so we can see this is the average length. So we can see the quantile regression. Quantile regression, you can see the minimum is very small and the maximum is very large, right? And so we can see, and also this CQR, the minimum is more larger than QR, and the maximum is maybe will be similar, and the mean and the average length for the quantile regression will be 5 point something, and CQR will be 12 or something. And also, so from this quantile regression, we can see this is the heterodastic, right? Because the small is very small and large is very large. So we can see, but the CQR, it will be the CQR maybe will be more conservative because we can see the minimum is significantly larger than QR. But the ICQR is more adaptive because it understands that the actual data. It finds that the actual data is actually heterodactyls. So actually, the standard error it will be very large. So you'll find that this average length actually standard error actually will be very large. So you also find that the minimum and the maximum will be very similar. Okay. So also we can see on the coverage. So the QR here, although the QR and ICQR looks similar, the minimum looks similar, and maximum is similar. But we can find the coverage. The minimum will be 0.33, 33%, too small. Even the maximum only 82. So quantile regression maybe will not good. Also the CQR, although the minimum and maximum and median, they are very close to 90%, but we can see that this average length is conservative. But the ICQR, so although ICQR looks similar, the average length of ICQR is similar to quantile regression, but its coverage is very close to 90%. That means it will be close to the actual needs and actual situation. So we can find it. So we can see this paper. So this picture. So this line is true value here, and this gray one is ICQR. So we can see the ICQR is included more true value here. But okay, so this is the first one, and the second data, Boston house prices. Yes, it also has the similar results. This is the feature importance, and this is the explain variance. So in here you have the 18 clusters. So it also has the similar results. So the QR and the ICQR are adaptive. The minimum and the maximum are similar. Also, and the ICQR I think is more adaptive because the maximum is become to 44. And the standard deviation, it also shows that the ICQR is larger. But also the coverage is, the ICQR is also better than the QR. And it looks similar to the CQR, but the CQR is not adaptive. So we can see the ICQ. So we can, from these two data sets, we can find that ICQR is the most adaptive prediction methods to the other three. Yeah, the other one is back sharing. So this is the feature importance. We can see this. I think these only two have the importance. The one is 0.2, the other one is 0.8. And the clusters, you have five clusters here. And so I think this is the oversized results, because the QR here, the minimum of QR is larger than the CQR, also the ICQR. And the maximum will be, it is also the largest one, 35. And also we can find a standard error. I think it's 2.11. and so we can find, but also the QR is very large, so the minimum will be only 8%, and the maximum will be 100%. But the ICQR is very average, is very close to 90%. So we can get the results. So the first two data sets, the QR is constantly undercover. And also the ICQR is more adaptive to hydrodactics in comparison to CQR. It has a higher standard deviation of the IQR and lower median, and is still ensuring the same coverage. So the last one is QR is overcoming, and the ICQR is bound increase lower than CQR. Hence, it is more adaptive. So, okay, also, let me explain again. So, the QR is overcoming. So the IQR and the minimum and maximum maybe will be too large, but actually will be not too large. So also the ICQR, so the ICQR, although they were not too large, and the coverage may be a little smaller, because the quantile regression, maybe the maximum is 100%, but the ICQR maybe will be smaller, but most of them is around 90%. So it is very close to 90%. So this is the best performance for each methods. So okay, so this is my sharing for this paper, and if you have more interest for this paper, you can just find it. Okay, so because this paper just published, I think it's from last month. Okay, very new paper. Okay, so this is today's video, and see you next time. Bye.